Hello everyone. This is Dilleswara Rao from Aeronautical Engineering Department. I've been giving you classes on automatic control of aircraft on the series of classes we have already discussed on last few videos. So today we are going to discuss on displacement of autopilot. So till now we have discussed equations of motion, longitudinal equations of motion, and solution of equations of motion, and what are the aircraft body axis system and earth axis system comparison. And when we are talking about that solution of equation also, how that equations have been solution and what solution have been derived for that, and that solution we got two types of modes of operation, that is short period mode and period mode operation also we derived in last classes. So now after making it here these things are discussing about these things are discussing about uh, when a control surface is being designed for an aircraft, how that control system should be designed and what are the signal strength it need to be given to any control system. So that has been discussed here. So let us go into the topic. So now today's topic is this displacement of autopilot. So see here, uh, uh, we have to say autopilot means, first of all, just make a broad introduction about this one. Our autopilot system is being integrated in every passenger and fighter aircraft. It has been a very sophisticated system that will gives you that less. It will be like a full-fledged automatic control system. So that will be given. That will be installed. With the integrated flight data system that using the integrated flight data system. So that by using that flight data system, how every system, every instrument, every option or every control system, how it should be operated, what is its operating condition, in which way that operating conditions should be changed, and what is its ultimate points, how frequently we need to check that, what are the feedback of that system, and if at all anything is happened inside the flight while the control is not in the pilot's hand, so then this autopilot system will give some it's an additional it's an additional aspect, so that will make the pilot to feel free, and he can get a feel of his operation, and how that piloting will be drastically we can increase the more safety and more reliable things for any aircraft. So that has been for that case only this autopilot system has been developed in every aircraft. So in the name of the name autopilot only, that is giving to every system is like it is a sophisticated system. It will be like a central monitoring system. So that central monitoring system will measure everything perfectly, and that measurement also will be very accurately it will take, and how much signal you are giving, that much signal should be accurately it will be go to that respective system, and according to that any changes have been needed for that. So that changes will be automatically, the system only will integrate the changes, and it will operate the system. Okay, so just see here one type of autopilot, it is like an electronic system only. So you can say like it's an electronic system, and with a software integrated thing. So this is a very like your unique system for controlling all the controls of aircraft. So here you see simplest form of autopilot system that has been still using in some transport aircraft. So that is called displacement autopilot. So this autopilot was designed to hold the aircraft straight and level flight with little or no maneuvering capability. Whenever the maneuvering capability also been integrated for integrated to this autopilot system, so that that operation also will be smoothly it can deal. So see here, one simple block diagram of autopilot system has been given for some operation that is called elevator operation. So here you see the theta reference, the reference values have been given to that vertical gyro system. So that gyro system is producing one signal voltage that is called EZ, and that is being amplified by the amplifier. And from that amplifier, that signal will be transmitted to the elevator servo motor. So their servo will operate the control surface, like aircraft dynamics control systems will be integrate that operation, how much distance it will be moved by that one, and then that operating signal will be transmitted to the control surface here. So here you see there will be some backend connection also there. Like whenever we are operating that one, so when the measurement condition, I mean how much signal you have given, that much signal is already operated, then that feedback will be again giving to the vertical gyro, and it will say like stop your stop your this is the end point of your signal. So from here there is no way of doing forward. Like you see, when we are operating a door, if you want to close a door or open a door, the door will be totally open, and if there is any stoppers are there, so that the stopper will gives you some message like, yeah, the door will be opened up to here only. After that, the door will not be opened. So that means that they are giving one feedback message to us. That means this is the maximum operating condition. So like that here also, because the aircraft is a very big object, so everywhere pilot can't feel the. He needs to feel the control surfaces. So for that purpose only, one feedback signal also need to be there. So that feedback signal will be given to this one. So for this type of autopilot, the aircraft is initially trimmed to straight and level flight. So the reference aligned, and then autopilot is being engaged. So if the pitch attitude and varies from reference, a voltage EZ is being produced by the signal generator on the vertical gyro. So this voltage is then applied and fed into the elevator servo. So that has been just given. So that elevator servo can electromechanical or like a hydraulic, like a servo motor will be like a it may be like a electromechanical, so like a mechanical motor, or maybe like a hydraulic operation. So the servo then positions the elevator, causing the aircraft to pitch about y-axis, so that returning it to that desired pitch altitude. So that elevator servo is then in general at least a second order system, but if properly designed, its natural frequency is higher than that of aircraft. If the damping ratio high enough, then the elevator servo can be represented by the sensitivity multiplied by the first order time lag. It's like like you see here, there will be whenever we are giving a signal to that one, the signal will be like a integral or differential function. So that differential function will be solved, and what are the roots of that function only will apply for the further thing. So the representative characteristics times vary from 0.1 to 0.03 seconds. The transfer function used to be represent the aircraft can be complete 3 degrees of freedom, longitudinal transfer function. The transfer function of the short period approximation, like short period approximation function, also we have just seen now, like how that short period function will be derived from our original equations of motion. So like that the thing will be goes forward. So like if some fixed external movement, some movement is being applied, so resulting a change of trim, that for example we have an error of 8 to generate a voltage to driven a elevator servo, so producing an elevator deflections to balance the interfering motor. So like we are, whenever we are giving giving to, we are ready to move that elevator by a by a signal. So if that signal is being not fully integrated, or maybe that signal is having error with them, so then what will happen? so that that error will be modified in between the system, so that the correction will be applied to that ultimate thing. So here you see another block diagram for transport aircraft. So here also that same thing, that the voltage will be applied to that amplifier, and from there that signal will be given to that another thing. So here you see that the short period approximation having a function in terms of yes, yes, and Laplace operator yes. That here you see s plus the 3.1 divided by s into s square plus 2.8 plus 3.24. So here this is in a Laplace transform operation. So here the Laplace operator roots will be the value. That means that is the transverse response of that aircraft that will be given to that control surface. So that has been given here. So that amplifier and the elevator servo are combined into some block, and then the vertical gyro will be replaced by a summer. So this is a summer. Summer means like that signal additional thing only. Okay. So one disadvantage is, I mean, if you the autopilot system is a full established thing, but one disappointment or disadvantage of this thing is, if you see that root locus system of an transport aircraft. So that root locus of transport, that means this root locus, how we got it from that that elevator servo function is there, no, that this one. So here in terms of S and CG. So if you give different values for that S, and if you solve the values for different values of SES, that is 77.5 and 8.8, like that. If give the values for that one, so we got zeta and omega NP. I mean zeta will be the short period approximation, omega NP will be the Fugite mode approximation. So here we are talking about short period approximation. The short period approximation, short period approximation locus is been designed like that. So if that locus is has been see here, there is a variation between the applied values. So see here. For a two different aircraft, the short period approximation for both aircraft are been given here. So this one and this is one. So for the first aircraft, it is a conventional flying at 150 miles per hour, and the second aircraft is a jet transport flying at 600 feet per second at 40,000 feet. So after the aircraft transfer function is negative, the sign of elevator servo is transfer function is made of negative, so that the forward transfer function is positive. So this is a like a positive with that 8 reference value we have given, no? So causes a positive change in 8, so which will be helpful when that glide slope control system is being designed for that one. And if the sign transfer function of that elevator had been left positive, so in the sign at the summer for the feedback signal would have been would be like a positive value only, so that the sign of the open loop transfer function would have been negative. Like here you see the feedback should be generally, the feedback signal will be normally it will be negative feedback only, but if the sign of the transfer function is suppose positive, and the sign of summer of the feedback signal will also be positive, so that the open loop transfer function would have been negative, like that the open loop feedback function sign will be like a negative one. So if this will happen, that short period oscillation for that aircraft is well, I mean generally it is well damped. That means well damped means if we are giving that if we are giving that a value to that function, so that it will be damped so much, but the damping ratio is about 0.78. So see here the damping ratio we can get it from that values of zeta. So as SES is the gain of the elevator servo is being increased from 0. Like SES is being increases from 8.8 to 77.8. Like that, if it is increasing from 0, so the damping increases, and then that means the damping increases. The damping ratio will be decreases 0.6, and the damping ratio has been decreasing. Like see here, the damping ratio is been decreasing to here 0.06. So it is like a sufficient values for getting the sufficient value for getting the stable condition. So another one, like this is also like a jet aircraft block diagram of an displacement autopilot. So this is also same as the previous thing. So here also one Laplace transform function. So this function, how we got this function? I mean, if you remember previously, that short period approximation and fugate point approximation solution, that solution of that differential equation is being did with using the Laplace transform of that. We have used that Laplace transform for changing the differential equation into algebraic equation. Then that is been did with the this Laplace transform S. So here, one block diagram of jet aircraft thing I've given. So another figure you see in the next slide. So this is the root locus of that jet aircraft that has been given in previously, that block diagram. If that function is like that, so for this, that root locus will be, that root locus means what? That yes roots only. That yes roots only we are changing from. If you see previously, so this has been near to 4. So see here, it has been that locus has been near to 4, but here you see it has been getting decreasing. So that has been can see like the root locus of the jet damping ratio, which is already too low for the satisfactory dynamic response. For the that means decreases rapidly as with the SES. So if SES is increasing, so it is being decreasing. So another consideration value for SES for instability, that aircraft for this SES is 77.5 degree per volt, and the second aircraft value is 38.4 degree per volt. So this degrees is what? That theta values only, that theta reference values we are giving output to that one. So for that values, we are getting the response of that frequency is this much. So see here the root locus of that jet transport function. So here the root locus has been somewhat decreased compared to the previously results. So for this example, the displacement autopilot, while satisfactory for conventional transport, but it won't be satisfactory for jet transport, because yes, the frequency response is very low due to comparing to that applied SES values. But for transport aircraft, yeah, it is a very big object, so that this much of frequency response will be automatically get into the stable position. That means that short period approximation will be that short period frequency response is being getting low, so that it will be come into that stable position very easily. But for a fighter aircraft, it is a very lighter weight aircraft, so it won't be come to it won't be come to that much early. For with a small response changes also, the frequency response will be very high, so that it won't be come to the stable position in that much easily. So that means it is not applicable. It is not be advisable for that fighter jet craft. So the S is operating by a values like dropping the gravity term, that CW sin theta. So if you remember this equation is the equation of motion we have derived for we have derived in our last few classes. If you see that the previous videos, you can get this equation how it has been used. So here that CW sin theta value is there. So if it is the theta is getting very low, it is tending to 0. So that these values also will be tending to 0 only. So for this reason, that the system shown in figure 2 and 4 are technically like a type 1 system. So for this one, like this one, and this autopilot system, and this jet transport autopilot system. So this will be comes for that theta value If it is that theta naught value is not 0, so that means that s in the denominator becomes a real pole near to the origin, so that um, uh, the things will comes on type 1 systems. So if in the case of jet aircraft, it is been designed to increase the damping of a short period oscillation. This can be accomplished by adding an inner feedback loop in utilizing rate gyro. So below figure will show that block diagram. So root locus analysis is been presented here to show that effect of rate gyro feedback. So see here, there will be a small inline, I mean local feedback system is been given here. So normal conventional one will be like what from vertical gyro, and it will go to that signal to amplifier. There it will amplify and giving to that elevator's servo. So after that it will it is being controlled by aircraft dynamic integrated system. Then that signal will be going to the control surface. But if while going from that elevator servo to that theta, if sometimes that values have been very less values also, you can see there is a more frequency response we are getting. So that is been advisable for jet aircraft, but it won't be advisable for the I mean jet means passenger aircraft, but it won't be like for fighter jets. So that has been given I mean for the transport aircraft, it has been not advisable. So for that, what we need to do, so see here, sorry. So here you see, we have given in internal feedback loop to cover this elevator servo and dynamic system. So with a rate gyro, so rate gyro feedback is been given, and summer is been given again here. So I mean, if this rate feedback is given, so that for a jet transport thing, so that STEM, I mean SEMP function is being given here. After that, it will go to that summer. From there, that integral function has been designed like that. So for that integral function, that has been looped by one rate gyro function, that is the SRG. So the SRG will be the rate gyro function. So that will be given like a 1 by s value, 1 by s function. One more 1 by s integrator is being given here. So from there, that function will be given to that control surface. So again here also one more feedback will be given. So that feedback is for completing, for knowing the completion of that operation. So for this, the root locus you see here. So for the, here you see the root locus for that inner loop as the rate gyro sensitivity is being increased from 0, and seen in figure 8, the rate gyro sensitivity is all like a real roots only. That this JW will be like a imaginary roots, and this is all real roots, but that will be even though negative values, but is the here you see that our SRG will be like we are getting 1.19 for a value. So for an aircraft having values of 1.19 value and 1.98 value, how that aircraft root locus has been almost like a straight, like a straight, there is no much deviation between that values. So which much deviation means it will be like a linear. So linear values means what? When the value is increasing, that response also been increasing. But here you see that the response is almost constant only. So like it's a curved function, it won't be constant, but that response between the values are very less. So that equation is now arises a value like a rate gyro sensitivity should be used to obtain that best overall system response after closing that outer loop. So there is no simple rule to aid the engineer in selecting the final sensitivity. The final choice usually results in a compromise between desirability, like a rapid response, and desire to reduce excessive overshoot. So for this illustration, two rate gyro sensitivities are been chosen. So that has been given in this one. So like what it is saying. So when a rate gyro sensitivity is a matter of matter here. so that the best overall system response after the closure loop will be given for this function. So there is no, I mean, for an engineer that selecting the final sensitivity, the final sensitivity choice will not be like a results in a comparison between that desirability rapid response and the desire to reduce the excessive overshoot. So excessive overshoot means while giving that signal, while we are giving that signal somewhat, you can say that signal is overshooted or being a delay on giving that signal. So that time what will happen? So if there is a delay on the signal, or else if it any objection is in the signal, so the things will be like overshooted. That means overshooted means whenever it is required, that time we are not giving that. That time that operation won't be there. So operation will start after some 1 or 2 seconds delay. So if that 1 or 2 seconds only, within that, if it is delay is there, then what will happen? So there will be many changes will happen on that operation. So for example, you say when an aircraft is about to land and about to land, that landing gear is not open. So within 1 or 2 seconds after, I mean, if it is approaching to ground, it is not open. After approaching near to the ground with 1 second delay, the landing gear is been open. So that time what will happen? That landing gear will, that time the aircraft is almost coming to the ground. So that time what will happen? There will be damage to the landing gear system. So that is called that overshoot signal. The overshoot means when required position, it is not that operation is not going on. So it will operate after some time. So after some time means that's not like a big delay. Even if a 0.1 second or 1 second delay also, it will be give a drastical damage. So see, like you're seeing that open loop poles, the root locus can now be drawn for each rate gyro sensitivity for a open loop. For each root locus, the value of amplifier is sensitively required to reduce the damping ratio to zero point 0.6 to 0. That is been tabulated here. So for this, the root locus values for jet transport autopilot for a 1.19 and 1.98, how that root locus values are being given here. So see here that root locus has been almost coming to that 0. So here the damping ratio is the damping ratio has been reducing from zero point 0.6 to 0. And here also it has been if that value has been SCF value has been somewhat increased, so it is been almost near to this locus region. So that means here you see there is a locus region that has been near to that function integrator also. So this is like a this like asymptotic functions. So the asymptotic curves only, but there is no comparison between that one. So see here that the result of the root locus study has been illustrated that the higher gain value of inner loop, that higher the allowable gain for the neutral stability of outer loop. So however, too high inner loop gain results and higher natural frequencies and lower damping as the inner loop poles move out along with 90 degrees asymptotics. So that is 90 degrees as asymptotes are been placed here. So that means for the values of SEG, that damping ratio for 0.6 and zero point 0 are changing like this. So that displacement, the displacement autopilot with rate feedback are adequately control the jet transport. It is being desirable to obtain a type 1 system to eliminate the steady state error for a step input. So this fact plus desirability of more maneuverability, especially for a fighter aircraft, is less to like a pitch orientation control system with control stick steering. So that pitch and orientation control system also, that here the theta values only we are depending on how much things are being given. Like see here that amplifier sensitivity required for TO, that TO or the conditions to require indicate for displacement autopilot, that two values of rate gyro sensitivity, that two rate gyro sensitivity values are this one. So for that values, so what are the frequency responses of that functions only we have given. So here what they are saying, for a transport aircraft, it is been desirable to obtain that system, and desirability for more maneuverability, like for a more maneuvering operation. So especially like fighter aircraft, so that pitch orientation control system are been defined for making some changes to this control system. So that will be, we will see it in coming classes. So this is all about this displacement autopilot system. So mainly that the displacement autopilot system is been designed for, this has been designed for the frequency response, for finding out the frequency response of that operating system only. So you can see that operating system frequency within a range of these levels, and it has been advisable to some jet aircraft, but passenger aircraft may not be accomplish this one. But there is a similar changes and modifications also been involved in this designing of this system. So that has been that has been updated to that pitch orientation control system. So that pitch orientation control system, we will see it in next video. So this is all about thing. So these are the reference books I've followed for this thing. So you can get your reference from these books. So that's all about this one. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.